today I'll talk about linear normal composition, and this is how the numerical with the Church, which was front of back and back up. Yeah, since the roots of numerical methodology, it became absolutely clear that one should focus on forecasting slowly evolving fields. And then it led to the realization that the slow field in latitude is governed by hydrostatic balance, and that led to the development of powerful models in series and G. And then this introduced the concept of the slow manifold, which is an ideal concept of a manifold on which the fast dynamics never depends. And I will talk about nonlinear normal mode decomposition, and the first classic nonlinear normal mode decomposition was developed in order to initialize numerical weather prediction models on the slow manifold. Right? And so there works on Packenhauer, Lees, etc. However, the classical nonlinear normal mode decomposition has inherent flaw. And when the model is initialized with a state produced by classical nonlinear normal models, and together with all the fast oscillations produced by gravity waves, you also get rid of all the tropical circulation. And that, of course, was a disaster, and so classical nonlinear normal mode decomposition is no longer in use in numerical weather prediction. So there were numerous attempts, which are mostly ad hoc, to save this, but this idea of ad hoc approach never took on. And so, in principle, the questions that we are trying to tackle is whether one can actually effectively separate fast and slow dynamics in the atmosphere without damaging the tropics in the process. Right? And so, in principle, the question, the answer to that question is yes. So, we found a way, given a speed limit, we found a way to separate the flow into components that, at least for a short time, would propagate under that speed limit. So there would be no phase speeds about it. However, it's not entirely clear what this speed limit should be. Right. So this new NNMD algorithm is based on the variational formulation in the normal mode framework, and in principle, I don't mean it specifically for the purpose of numerical normal mode, NWP model initialization, but rather as a tool to analyze fast and slow dynamics. All right. So I'm sure many of you know the linear normal mode decomposition on the sphere, and so I will be brief here. The most important fact about linear normal models is that they are directly associated with Rossby, IG, Kelvin, and Rossby gravity waves, linear waves. And the second important part is that those waves produce an orthogonal basis. And so I can expand the circulation field over this basis. And when I've done so, I transform the original primitive equations on the sphere into the spectral ODE that has a very special structure. So the linear part of this, so I'm talking about nonlinear primitive equation. And so the linear part of this will be given by diagonal matrix with eigenfrequencies of the waves on the diagonal. And there will be a right-hand side, which is given by interaction between the different waves. Right? So, and when one looks at the linear normal modes and linear frequencies for the fixed equivalent depths, one sees that there is a clear timescale separation between various normal modes, with exception of two tropical waves. This is Kelvin wave over here and MRG over here. Oh, you don't see my... Okay, thank you. Then, yeah, so you can see that there is clear timescale separation with exception of those. Like this one is called MRT, and such separation is persists for every equivalent depth. Yeah, so if you could get rid of those two waves, essentially there would be timescale separation, and you would know that you can achieve separation for the whole flow. So, but that seems like a minor inconvenience in principle, and gives a hope to do the separation in the global model. Right? Now, I want to be clear about two concepts. So there are concepts of balance, and there are concepts of speed. And in principle, in the linear system, they are almost synonymous, because the Rossby waves, here you can see the Rossby wave. So here you can see the Rossby wave spatial structure. The Rossby wave is balanced and it is slow, while G waves are unbalanced and they are fast in the linear system. However, in the nonlinear system, this synonymous thing is no longer there. So in the nonlinear system, in principle, the balance is a structural concept, which is some kind of extension of the geostrophic balance to the more general setting, could be to the equator, or could be to the, from linear to nonlinear system, while the fast and slow, to me, refers to how fast the wave propagates, right? It's a dynamical property of the propagation. And so for us, when we talk about in the nonlinear system, there are two ways to look at the gravity waves and the Rossby waves. While one can take the speed of the wave as a determining factor, and then the gravity waves are always considered fast, and the Rossbys would be always considered slow. Or one can take a structure of the wave as a determining factor, and that is the approach that we take. And so for us, the Kelvin wave is what you see over here. It's a spatial structure. And same for Rossbys and MRG and any other wave. And so with this paradigm, an IG wave can be slow, and the Rossby wave in principle can become fast. So don't be shocked when later on in the talk I will mention the Kelvin waves that are nearly stationary.
See, this is not fair. This is only for deep mode, I think.
Exactly. I specifically put there the modes, and actually with a reason. I put there the Rossby MRG waves, etc., for large equivalent depths, in order to give you a hint how connected the tropics and mid-latitudes are. Right? And that's my next point. So if one wants to separate fast and slow dynamics in the nonlinear system, that separation should include the tropics. So all right, so let's first recall the classical nonlinear normal mode decomposition, and so the purpose is that if you have some state W, you want to find a balanced state which depends on this W, which would be close to it in some sense, and when the nonlinear model is initialized on this state, it would evolve slowly, at least for a short time. And the classical method achieves this by setting decomposing the initial state, or this full state omega tilde, into Rossby and IG component. And then the Rossby component is kept because it's considered slow by default. And IG component is found from the balance relationship where the derivative of the corresponding coefficients are to 0. So this IG component would be stationary in the initially stationary in the slow so defined balance, right? And so in principle, classical nonlinear normal mode decomposition achieved what it was supposed to do. It produced the slow state, right? But it paid a heavy price for that. And you can see the price over here. So these are two mixed Rossby gravity and Kelvin wave that were left out after applying the classical nonlinear normal mode decomposition to the initial state, which has the same colors, however, with axis at the points. So there are several orders of damping applied to tropical circulation in classical NNMD. So, but maybe one can argue that all right, we killed Kelvin wave, but this wave was fast, and so it should not belong to the slow manifold. But now we are looking at the recent article by Katarina Holuben, and so what we see over here is just filtered Kelvin wave propagating in time, or not propagating at all. Right, and after additional analysis, you can see that the large percentage of Kelvin wave variability belongs to the structure that is actually spatially stationary. Right, it's a standing wave. It's not only the standing wave, but standing wave is a large component of Kelvin wave in reanalysis. And you can see this structure over the Indian Ocean plotted on the right plot. Yeah, and so the conclusion of that is that classical NNMD is not a good way to separate slow dynamics in global nonlinear model, because the premise on which it's based is that nonlinearly slow state is a small perturbation of the linear one. And that is not always true. Right, so let's look at the new NNMD and whether we can improve on that, on the classical one. And so the purpose is the same. The purpose is to separate the slow and fast propagating component. However, we are doing it based on different approach, instantaneous phase. So what is instantaneous speed, phase speed? Well, when suppose I have a nonlinear wave, and I'm not specifying what kind of nonlinear wave, this is just a general nonlinear wave ansatz. And so then I can compute its instantaneous frequency like so. And the instantaneous phase speed by dividing the instantaneous frequency by the wave number. right? And so what one sees is that the instantaneous frequency of the linear wave, of the nonlinear wave, is given by the linear frequency and the contribution of nonlinear terms. And so even if the linear frequency is fast, the nonlinear terms can in principle compensate that if they have the right size and sign. Right? And so we reformulate the problem in a variational way. So mu and NNMD, we attempt to find the closest state to the W tilde that has no instantaneous phase speeds exceeding the imposed speed limit. Right? And so this is the same restated in mathematical terms. And that is a quadratic optimization problem with cubic constraint. So cubic constraint comes from the fact that this term, imaginary part of nonlinearity times spectral coefficient conjugate, is cubic in spectral coefficient. And so in principle, this problem is difficult to solve because of the large number of degrees of freedom. And you have the same number of constraints as number of degrees of freedom. And then there is another complication that essentially computing the gradients and Hessians of the constraints is out of the question because it would just take too much time. And so the standard FAIR algorithms for the interior point of conjugate gradients that you use in optimization just couldn't do here. However, there is a trick that allows to solve this problem. So let's assume for a moment that the nonlinear term does not depend on the state vector of the coefficient W. Right? Then the problem uncouples into m sort of one-dimensional problems with two constraints. And those constraints one can recognize as circles that are touching at zero. So they are touching at the origin. And this problem has an analytic solution. So I wrote it down here, but you don't need to read that because I'll show you the solution graphically on the next slide. Right? And so once you know how to solve this simplified problem with n non-depending on the state vector W, then you can set up the iterative procedure that would so you set initially you set your W to the target state W tilde, compute the nonlinear terms at the state W tilde, and turn on the crank. And so to account for the fact that in reality n does depend on W, you take not the optimal solution, you take the solution with some small slack. And that turns out to be enough. And so the resulting algorithm is very cheap because it requires just one nonlinearity evaluation per iteration. Right, and so here is the solution of that optimization problem for a single mode. So this is a situation that is typical for these propagating gravity waves. So the frequency is large and positive. Right, and so then the constraints are given by two circles, and the admissible set is in gray. And you want to find the W that is within the admissible set and is closest to the given W tilde. And the solution, of course, is just to project the W tilde onto this larger circle. And what we do, we just step out a little bit. Right? And what the classical NNMD would choose in this case is so there is a line connecting those two circles, and it would choose a point somewhere here. on this line connecting this circuits. And so this is what we call, so this is stage one solution. In principle, we formulate this algorithm in 3 stages. So at the ambitious stage, we essentially adjust each weight according to this optimal procedure. At the second stage, which we call conservative, we stop adjusting the loads that are already within the bounds. And in third stage, we clean up, set to 0 all the weights that have too large phase speeds. And so let's see whether it works. But it does, because otherwise I wouldn't show it. So here we are choosing, so here is what is the data. So it's ECMWF forecast at T120 resolution, 137 pressure levels. And so the number of degrees of freedom is more than 1 million. All right, and so here is how the algorithm works. So the first plot shows you the integral, how you satisfy the bounds integrally. Here is the formula, which so you see that originally, so it's the first step. There is large violation of the constraints, but algorithm converges to the state where there is no violation at all. And the third plot shows you the maximum phase speed in the slow manifold. And you can see that at the end of the algorithm, there are no phase speeds exceeding the imposed speed limit at all. So the algorithm completely converges within about 30 iterations. For various speeds, so here we have 100 meters per second or 50 meters to 5 meters per second. Right, and so now let's see what it does to the dynamics. And so we see that. So first of all, those speeds are not randomly chosen. So 100 meters per second cutoff speed is just above the highest two Rossby, and one phase speed at the equator. So that's a sensible upper bound for what one would consider might be slow dynamics. Right, and so we see that all the Rossby field is retained with cutoffs of 100 meters per second, 50 meters per second. But at 25 meters per second, you already start losing something in the Rossby field. And but for AG, the situation is somewhat different. So there is a gradual progression of IGs from 100 to 50 to 25 to 5 meters per second. So there appears that there is no intrinsic cutoff that would tell, okay, so it's sensible to call 50 meters per second dynamics slow, and I don't need any other cutoff. So there is no speed gap in the nonlinear system. However, the large part of the IG field is propagated as slowly as the Rossby. So especially for 50 meters per second. For 5 meters per second, the story is different. Right? And now let's look at the tropical circulation. And what we see again is that at 50 meters per second, we essentially retain a complete Kelvin wave. At 25, we still have a lot of Kelvin wave left, but it's severely dampened. And even at 5 meters per second, there is remainders of Kelvin wave, and it's much larger than what classical NNMD has left us. All right, now let's look at the movies. And so this one shows the 15 meters per second decomposition because essentially it's the one that contains all the rows. And the top panel is full field, the middle panel is the 50 meters per second slow field, and this is the fast one. And the fast one looks like noise. It is not noise. There are some identifiable structures there. So, for instance, the structures within the jet are exactly in the position where there is strong curvature in the jet, and that suggests that these are waves that are accelerated by the centrifugal forces and become too fast for the speed limit imposed. And I'll show you there are other things that are in physical and fast circulation, but the slow circulation is essentially identical to the full one, almost identical, right? And now let's see the comparison with classic NNMD. So this is the full IG field. And the next slide is new NNMD field with 50 meters per second cutoff. And this is what the classical NNMD does to the poor tropical circulation. So it leaves almost no trace at all from the tropics. All right. And so what are the two differences? Well, tropical circulation obviously is one. In the slow IG, second, there are orographic standing waves, and third, the amplitudes of the hydrostatic circulation in the jet is higher for the new NNMD. So one can see that these lines are almost parallel, which indicates to me that the sliding involves in the classical NNMD essentially artificially reduced the amplitude of the slowly propagating hydrostatic circulation within the jet. However, in the tropics, the situation is of course much more dramatic, and almost all tropical circulation is slow. Not all, but most of the tropical circulation is retained. And now let's look at the Hofmüller diagrams for various cutoff speeds and see. So this one represents the slow IG, and you can see that the slow IG imputed with this method is yes, it doesn't propagate fast. And on the right, you see the fast IG field for the 100 meters per second. So this should be very fast waves, and one can clearly recognize tides of it. As it should be, because tides are faster than 100 meters per second. So, this is just an example of, and so this is a bit of philosophical discussion. So in classic NNMD, there is a slavery concept involved, where one chooses Rossby's as a slow variables, and IG waves are slave to the Rossby by some kinematic relationship, right? But in NNMD, formally Rossby and IGs are treated the same. So there is one computes the slow field for the Rossbys exactly by the same procedure as for the IGs, and so formally there is no difference. However, factually, the nonlinear terms are dominated by Rossby and Rossby flow interactions outside of tropics. But that cannot be this cannot be all, right? Because if it was so that it also should be shown in the classical, so it appears that in principle, true classical true slow modes should also contain some contribution of IGs and tropical circulation. So NNMD is not balanced model explicitly. We don't impose any balance on NNMD. However, it could be that it's implicitly balanced model, and in that case, Rossby IG and Rossby Kelvin wave hybrid should be some new slow variables in this balance relationship. And so the algorithm works because it is able to quickly lock on to this intrinsic slow state that dominates nonlinear interaction. And my hypothesis, of course, is that it contains Rossby plus zonal mean for the mid-latitudes, and the equatorial waves retains the tropical state. So, yeah, so I will skip yeah, I will skip this slide. This is just an example of what can be done with this new method, and a lot can be done. And so I'll just go to conclusion. So the first conclusion is that the wave propagations in the atmosphere are very different from the ones predicted by the linear theory, which you could see in the field that produces, and in general the atmosphere is slower than for whatever reason. Our new method allows to separate the flow according to the wave propagation speed without imposing any sort of underlying timescale separation. Right? And we see that there is no timescale separation for task either. And finally, the algorithm is practical. So on the laptop, those 30 iterations, 42, you can run this on laptop and it will converge within 30 seconds. For the serious resolutions that we used, one needs 1 hour on the line to 1 time. Not one iteration, but 1 time. So, yeah, and it always converges in practice. However, there is no proof of convergence. So I am done.
Thank you very much.